All right, it's a pleasure to be here today to talk on a topic near and dear to my heart and to give this talk for George Craford. And today I'm going to talk about the start of the field in LEDs and how that has progressed to today what is an ultimate lamp. And in this talk, I'll give an overview of lighting technology in general and some of the early work on electroluminescence and LEDs. We'll talk about Nick Holonyak's contribution and its impact on LED technology, and then progression of technologies to the status of LEDs today, and then finish with some ongoing developments in the field. So this is a chart that shows some of the history of lighting technology. And one of the things that George points out when he gives this talk is that for the first tens of thousands of years, we used fire as our source of light. And then there was a period, and that was very inefficient, something like 0.1% efficient at best. And then there was this period of time in the 1800s where gas technology was used for lighting. And that provided a modest improvement in efficiency, but that was widely used for most of the 1800s. One of the most significant advances that came for over a number of centuries was actually the invention of the incandescent bulb. And that, in combination with fluorescence, really took us through most of the 1900s. But it was really in 1962, with Nick's development of direct band gap LEDs, that we really started the progression towards the ultimate lamp. And what we now have today is a world that is predominantly lit using solid-state lighting sources, LEDs, and to a lesser extent, OLEDs and lasers. But for the foreseeable future, there is no technology that will challenge this ultimate lamp. So when you look at this in retrospect, there's this period of tens of thousands of years where we had fire. There was this little period of time where we had gas lamps in incandescence and fluorescence. And then there'll be this long period of time where we have solid-state lighting. And that was all started with Nick Holonyak's LED work in 1962. Before 1962, there was a number of work in electroluminescence and semiconductors. This was both in silicon carbide and gallium phosphide. However, these were both indirect materials, and they actually didn't provide a path to anywhere, meaning they weren't a path to be built upon to realize what today is the ultimate lamp. That really started with Nick's work in 1962. And it was the direct band gap LEDs and lasers that he demonstrated that really lit the world on fire. And it is that work that really started an explosion of work by others in the field, because people, once they saw that, knew that solid-state lighting was possible. And you can see the host of companies that dove into the field and really started to work in developing solid-state lighting sources. So these are some of Nick's early and first LEDs and lasers. So you see on the left, you can see the gallium arsenide phosphide crystal and the laser diode on the header, as well as the cross-section of the laser diode shown on the left. The crystals on the right and the LEDs on the lasers on the right and the crystals on the left. Nick didn't only make devices, but he realized their practical value. So this is on the left-hand panel, you can see a article from Reader's Digest where he talked about the LEDs LEDs and lasers being practical, where in a year there might be indicators, and in 10 years lasers used as for lamps. And the point here is that he definitely realized their value of devices, and he also realized that they would take some time to develop. In fact, one of the things that you'll see is that it actually took quite a long time to develop, and that's a lesson that Nick would often teach students, that things really needed to be built upon and take time and have patience. And so some of the early LEDs are shown on the right here, and they were devices that were sold for actually around $100. The lasers were 10x that, so $1,000. But these were devices that were mostly good for laboratory use and experimentation because of their high price and still efficiency that needed to be improved. But as I mentioned earlier, many companies dove into this and worked on improving the efficiency. And by the early 1970s, there were real practical indicators and uses for this. And you can see an example of an LED watch as well as the HP calculator. So it took a little longer than Nick first projected, but things started to be developed and started to come into use for the world. From that time on, there was a progression of developments in LED technology, each increasing the performance about an order of magnitude, 10x every decade. So what I'm going to do now is walk through that progression of technologies that take us to the ultimate lamp, where we now have the highest performance lighting sources in the world now are those of LEDs. So after the gallium arsenide phosphide direct bandgap work, the next development was done by Monsanto of some of Nick's students, George Craford, Harold Korb, Dave Kuhn, and John Rossi. And the work that they did there was to add the nitrogen isoelectronic trap. And what that did was nitrogen localized the carriers very strongly in real space. And that strong localization created an uncertainty in momentum space. And so as a result, there was significant overlap of the wave function at k equals 0. So this effectively turned into a quasi-direct material. And with this, the efficiency improved 10x. And this technology, one of the things that George likes to highlight, was not LPE, was not MOCVD, was VPE. And these origins also came from Nick. Nick's work on LEDs was close to VPE, and he was the one that developed that for the gallium arsenide phosphide. And the work at Monsanto was to go ahead and convert that closed tube technique to an open tube technique. The marketing department at Monsanto was very excited about this work, and so excited that they went ahead and ran this ad in the Wall Street Journal. And this is an ad that George and Nick have talked about because shortly after this ad came out, there was a fairly well-known director from Bell Labs that, used George's words, accosted him at a well-known technical conference and told him it was technically irresponsible to suggest that LEDs could be used for headlights. Well, the good news is Nick and George got the last laugh. So this is in 2012 at the 50th anniversary of the LED. This is George presenting Nick with a Mercedes headlight. Since the late 2000s on, LEDs have been used widely in headlights on cars. The next step in the technologies was to move to taking the direct bandgap material and making lattice match structures. So this was aluminum gallium arsenide lattice matched to gallium arsenide. And this resulted in another 10x improvement in efficiency. So now we had red devices at about 10 lumens per watt. And this was important because it enabled outdoor applications. So this is for center high mount stoplights on cars and traffic signals. The other thing that was worked on was transparent substrate. So the original devices to be grown lattice matched were grown on gallium arsenide, but also transparent substrate devices were developed. The development of device structures and engineering of devices for extraction efficiency is very important, and that's one of the key technologies that also is critical for LEDs. So these technologies improved the field by 10x, but they had a problem. And one of the problems is that they were not very environmentally reliable. And that really limited their use and utility. So what was needed was the development of a new material system. And that material system was aluminum gallium indium phosphide. But to do that, new growth technology was needed. And that required metal organic chemical vapor deposition. And that technology was first developed by Manasevit in the late 60s, but was really brought into viable use by Russ Dupuis in the 70s. And Russ will talk extensively about MOCVD here, so I'm not going to go into that further, but MOCVD is the critical technology for crystal growth that is used to make all of today's high performance LEDs and lighting sources. So MOCVD growth enabled the development of the aluminum gallium indium phosphide system, and this system could be grown lattice matched on gallium arsenide and enabled us to go from 10 lumens per watt to 100 lumens per watt, so another 10x improvement in efficiency. The devices were first developed on transparent substrates, and again, some of Nick's key students and grant students were involved in this. And so those were George Craford. Also people that worked on this were people like Lou Cook and Virginia Robbins, both who were students of Greg Stillman. And then there were work on transparent substrate, so by removing the gallium arsenide and bonding the gallium phosphide substrate enabled transparent substrate devices. And Mike Crames, Nate Gardner, and myself all worked on that technology. And ultimately, more work was done on improving the devices for improved light extraction, and this led to the first 100 lumen per watt devices. And again, more students, Nick students and grad students worked on this technology as well, many of whom I just already mentioned. So now there was a spectrum of orange, yellow, and red devices, but blue and green devices were needed to round out the entire spectrum. So work on nitride LEDs was done in the early 70s by Pancove, but that actually was terminated and was not continued. But then Akasaki made key improvements that enabled the development of the materials and device, certain key aspects of the device. And that was then built upon by Nakamura to enable high-performance blue and green devices as well as blue laser diodes. And this ultimately then provided the full spectrum of devices from blue, green, yellow, orange, and red at high efficiencies. There is still a green gap problem where the efficiency falls off in the green region, but that is compensated for by the eye sensitivity, which still enables highly efficient devices at this time. Okay. So one of the things to recognize in LEDs is that they're very complicated structures. And I still remember when I first interviewed at Hewlett-Packard, I was right out of Nick's lab and spent my time at grad school working on laser diodes. And I made the joke that LED was just a laser diode that didn't work. Nobody laughed. But as I came to know and appreciate, they are very complicated structures. And if you look, we have devices layers that are on the nanometer scale. And active regions, barriers, blocking layers for electrons and holes, all that need to be managed in composition, strain, at the interfaces within the bulk of the structure. So it's really a optimization problem of thousands of parameters that need to be done to really make sure that you can make efficient and high performance devices. And that's true of the materials, but also true of the device structures. And this shows some of the work of the most efficient nitride LED structures. And this was done at Lumileds, and again by some of Nick's students and grad students, including John Epler, Mike Krames, and Oleg Shenkin, who was one of Dennis Deppy's students. And this is involved removing the sapphire substrate and forming a thin film flip chip on these devices, as well as managing light extraction. And there's lots of technology that goes into here in terms of how to manage light extraction, not just from things like roughening, but even from very sophisticated physics around how do you manage the interaction between a dipole within the active region and the light emission. Lots of device physics here. And as well as managing the heat and other mechanical and properties as well. So these are very complicated devices, even though you might think of them just as kind of a PN junction. They're not. Right? Now that the full spectrum of devices existed, still what was missing was white. And there's a variety of ways to make white. The most common way to make white is to use a blue LED pump and then a broadband phosphor to fill in the rest of the colors of the spectrum. Other ways are to use blue, green, and red LEDs directly, or possibly a hybrid approach where you use a blue pump, a phosphor, and then LEDs to fill in some parts of the spectrum. The predominant technology that's used today is the blue pump phosphor, and that's primarily due to the fact that the green and red LED spectrum still need to be improved. Theoretically, if you can get 100% quantum efficiency, you can make something like a 400 lumen per watt device using red, green, and blue LEDs. Today's phosphor pump blue devices are about 200 lumens per watt or more. So ultimately, you want to get to red, green, and blue direct emitters. But today, most of the world is phosphor pump blue. And this shows some of the highest performing devices. This is a Lumileds device, which is a power device, and at higher power operates at 180 lumens per watt, and at lower current operates at 220 lumens per watt. And this is this thin film flip chip device that we showed earlier. In addition to developing the technologies, you really need a family of technologies to fulfill all of the lighting requirements. And so if you look at the breadth of lighting requirements from indoor lighting to stadium lighting to spotlights and architectural, you see that you actually need different types of solutions in terms of efficiency, luminance, quality of light, control. And so that really leads to a significant family of products that are required to support the lighting industry. And LEDs really are ubiquitous. People don't know the stadiums for the last few Super Bowls were lit by LEDs. The Times Square Ball is now all LEDs. And actually, solid state lighting has over 75% penetration of the entire market at this point. And that's shown in this graph. And for those that may not have been following some of the business sides of things, LED illumination only, not other markets, but the lighting part of the market only is a $30+ billion industry today. This market projection actually shows that it may fall off in a few other years. I think George and others actually think that that's probably not going to happen. There's still a number of applications that are emerging. I'll talk a little bit about some of those here. And there's still a whole replacement market too. Even though LEDs are solid state lights, they still at some point do need to be replaced. So some of the areas for future work are further efficiency improvement. And so this is both how to improve both the, in the case of the blue pump phosphor, the LED as well as the phosphor itself. The LEDs are pretty good. Some of the devices are, commercial devices are about 80% wall plug efficiency. So there isn't that much further to go. Maybe one of the bigger improvements are to use narrow band phosphors, which might improve the efficiency by about 10% or so. Another is to improve the efficiency at higher drive currents, and I'll talk a little bit about that in a future slide, as well as improve the efficiency across the entire visible spectrum. So we can go to direct green and blue and red, white light coming from LEDs. So one area for improvement is really how do you drive to high efficiency at high currents? And if you look, the devices, nitride devices have this characteristic where with increasing current, the efficiency rolls off. And this roll-off is due to Auger recombination. And again, this was work that was done at first done at Lumileds, where they discovered that really was Auger that limited this. And again, this was George Craford, Mike Crames, and Nate Gardner that led a lot of this work. And that led to improved device structures for improving the LEDs, but there's still trade-offs that need to be made that don't allow you to fully, at this point, conquer this effect, and it's still limiting the ability to have high efficiency at high drive current. So this is definitely an area for more research and more work. Other phenomena also limit phosphors, and again, at high irradiance, phosphor efficiency decreases. So this has led to work on new materials, but again, there's still room for more improvement here as well. Another area that is rich for improvement is in the area of microdisplays. And I'm going to talk about microdisplays first through the lens of headlights. So you might say, how do those two relate? So if you take an LED and you start to put it into a microdisplay in a headlight, and people really are working on these things today, you see that you really can do phenomenal things with the beam. So you can imagine where you're, here's your car, and you've got an oncoming car. But now instead of running at low beams when you see the car, what if you had high beams on all the time, and your LED micro display was smart enough to see, oh, I've got a car here, and I'm going to locally dim that area. Or if I'm going around a curve, I'm going to not just steer the light, but I'm going to sense where the road is. So if there's snow there, I'm going to guide you right where the edge of the road is to do that. So really the whole concept of really putting intelligence into the headlight is an area that's being worked on and developed. And these really points us back to that 1970s Monsanto concept. And so people are working at developing micro LEDs for effectively making displays out of headlights in cars. And so what is a micro LED display? Micro LED displays are taking LEDs and using them as pixels in an assembly, typically in the order of 2 to 50 microns. And what people ultimately are working on are to use these to make displays where you might be able to use them for your smartwatch or your phone. And these would ultimately wind up with pixel sizes that are in the order of 20 to 50 microns, or even micro display applications for augmented reality or virtual reality, which will take you down to the micron level. Really, the killer app here is the smartphone. So we talked about a $30 billion market for illumination. If you can make smartphones with micro LED displays, that's another $25 billion market and people are talking about that being a potential in the early 2020s. And people are actively working on this. Apple has an extremely large effort at trying to use inorganic LEDs to make micro displays to be used in smartphones. So in conclusion, it's really, where did it start? It started with the work of Nick and the demonstration of the direct bandgap LED. And what that has enabled is not just more efficient light sources, but light sources that really have the ability to put a large amount of intelligence in them and really change how we live. And those sources ultimately also have saved large amounts of energy, and in combination with OLEDs and lasers, which will have some application, will result in solid state lighting being the dominant technology in the future. Thank you.